we call it engineering. I don't call it engineering. I call it it's like art, guesswork, trial and error. So, and then it radiates. I don't know if you know who came up with this, Professor at Houston. I'll remember it in a second. The tall, handsome professor at Houston. Who remembers? Anyway, he was at Harvard when he designed this. Actually, he worked with R.W.P. King, the founder of the dipole antenna, and he wrote the first paper on this. And it's really interesting. So, what causes this to radiate? I was one of the luminaries in this field who designed tons of dielectric resonator antennas, and whose name is connected to this. I remember 2 years ago in the APS Antenna Propagation Conference, I saw him. We were like 5 of us standing. And I'm not aggressive at all, but I like to ask questions, I'm not, I said, so-and-so, you worked a lot with DRAs. He said, yes. I said, how does it radiate? He looked at me, I remember so, and you know what? Again, I'm not mentioning names, but even if but he said, Omar, what do you mean? It just radiates. I remember that.
I like that explanation.
Yeah. He said, and he looked at me in a very suspicious way, like, what is your intention? As if I'm a spy.
He sensed a hard question coming.
Yes, exactly.
He wasn't briefed for this.
It wasn't in the book.
So does he know, and others know how to these radiate, how to design them to work? Yes, they have some tricks. They pull it, they put this feed. So let's go next.
Yeah, so I have a question. I don't know if you can talk about this, but I mean, the material that is dielectric, that's not going to take any current, right?
That's what?
It's not going to take any current, right?
I'm going to come to that. You're looking
so I
into
guess
it.
it's kind of like doing one of these things. It's like, okay, you're coming out, but I'm going to make you go back.
You are in the right direction. And thanks to my question, I sensitized you to the right direction.
That's good.
So in the world of EMI&C, we see these figures, right? A lot. Designed to unradiate. I don't know about the English. Unradiate, okay? Non-radiate, unradiate. So we talk about very, very small levels. We know this. We talk very, very small, and we don't need to reach. Look, 316 dB microvolt, 316 microvolt. And it was an eye-opener when I worked with this. So the language, the physics is the same, but the culture is different. When you talk to regular antenna engineers, you tell them a transmission line radiates, they tell you, what's wrong with you? Of course it doesn't. The textbook doesn't, but next please. So if we look at the source of electromagnetic noise, thank you. That's the source of electromagnetic noise. When I worked in the industry, I love to classify. I have that colonial instinct, you classify, right? You classify, you control. So I was colonized, though I was never a colonizer. So if we look at the chip, the chip is, there's a package on the chip. Yeah, the chip exactly. And then the package goes underneath the heatsink. And then all of that mess goes there. And then all of that goes in the chassis. So it's a really complex process. What exactly causes what radiates, what's a secondary, primary radiation, and so forth. Now, many smart engineers in the EMC world, they know how to handle this. And I happen to work with really brilliant people without a PhD, without a master's, who really know quickly the physics of it. I learned a lot from those. I found out that there's a limit to my knowledge of equations. You see, the equation is good to get a thesis. Next, please. So, and these are coupling scenarios, the coupling between systems. On the left-hand side, remember the days when they used to be so picky on turning our cell phones off? Not anymore. Did you think about that?
Is there a reason because put the walls into place and folks are now more comfortable with the devices? Or
You know,
what?
I really cannot answer this, but I have my suspicion is that it's a combination of the following. If you look on the left-hand side, the latest, I was flying with this Norwegian airline, very excellent, cheap carrier, $300 to London. I couldn't get any communication when we landed because of the shielding is really strong from the glass. So look very carefully, they might be very fine grained. You know, it's headache.
A Faraday cage.
A Faraday cage, but not three-dimensional, but one side.
I think they have metallic flake in a lot of the airplane glass. There's something.
Possibly. There's something. I could tell because if you land in the old aircraft, from the air, by the way, you can get the signal.
If you're flying TWA or Pan Am, it's plexiglass.
Yes.
Okay.
You know.
That. I'm sorry.
It's sugar breakaway glass.
Yeah.
This is a cross section of the plane, and I had actually an interesting work earlier when we looked at the propagation of radiation. You see, many people think on the left-hand side they were worried about the coupling, but the coupling is not going to the cockpit. The coupling is so difficult. It's going through the glass or the plexiglass, and it follows the paint. If you don't have paint, aircraft like paint because it's a commercial advertisement, then it hugs a slight paint, gives you surface waves.
Like the water, like the top of the water.
Yeah, it's a waveguide.
Interesting.
If you want to
Yeah.
talk. And then it goes to the belly of the aircraft or the top where there are antennas. So now I cannot talk specifically how important it is, but these coupling, because they always say interference with navigational equipment. If you go to the front of the cockpit, Rockwell Collins makes all of these displays. These are shielded. I mean, you know, you can put a high power device and nothing will go through it. So it's the other coupling that is important because then you have interference with these navigational equipment. Yes.
So let me stop you a minute. So the antenna's on the outside of the plane, I'm assuming,
Yes.
for pilot to,
Navigation.
it's all to do with flying the plane.
Yes.
And
The,
your transmitter is sitting under a seat.
exactly. That's the human
So,
with a cell
so
phone.
how is my friend over here going to be safe on that?
Well, you see, but you see the noise, the transmitter.
Never mind the rest of us.
No, the transmitter will go outside, coupled to the antenna, right?
All
Coupled
right,
to
so
the
the
antenna.
box is sitting there, but in theory the box is not radiating.
No, I'm sorry.
The plane itself is like a Faraday cage.
No, the plane is a cage, Faraday or not, but it's a cage. And then you have the radiation coming to the belly or the top, and then you have something that also we don't look at like a non-linear coupling. So you can generate other harmonics.
So she can sit on top of that seat and be fine.
Everybody will be fine. I mean, they look, this is the probability. They want, 0.999999 probability that the plane will be perfect.
So you're saying there's a skin effect to the extent the radiation encompasses whatever. It's maybe affecting the antenna, perhaps, but nothing else.
Sorry, it's not a skin effect per se,
Okay.
but it is coupling through surface waves.
Okay.
Coupling through surface waves, exactly. Coupling through surface. If the surface of the aircraft is purely metallic, the surface wave is very little. Yes, there are, but very little.
But with
because
the paint,
the paint makes things worse.
It behaves like water, like a water channel.
It's
right
a
over
channel.
The water. Yeah.
It's a channel. Yes.
so is that a dialect? So
It's
if
a
I
dialect.
I have the surface, the paint, and then the air.
Exactly. So you have an interface, which is excellent for surface waves.
Right, which is
Yeah.
great.
Sit on the outside.
No, you shouldn't.
No,
You'll die.
This is why I sit in the aisle. Aisle
now we know.
So this one,
21D. That's me.
on the right hand side, you have a circuit board, a schematic of a circuit board, and we talked in the past and tried to advocate this generalized coupling, not direct coupling, but generalized coupling. So what is the message from this slide is that the coupling is not a trivial phenomenon. Okay, it is not impossible. It will follow the physics that we know, but how to know what couples is a different thing. Next. Okay, so next. So what does radiation mean? It is the presence of a field, next please. Static field, or is it a dynamic field? You see, when I talk about books and physics books and all of that, it's my career. I teach electromagnetics, and I'm not trying to tell them displace me or kick me out or have someone, or kill the field.
Or use a book instead.
Or use the book instead. I'm trying to tell them actually the book is the biggest problem. I don't like to use books, by the way. I like to use my notes. But is the static field a pure static field or not? I don't think there's anything called static. They taught us that there's things called static just to simplify the
So are you
Coulomb
talking
law.
about Gaussian, or you're talking about white noise, or you're talking about...
I don't think there's anything called static.
Okay.
Static means nothing. I don't think anything, there's none of it.
That's just
It's a simplification.
theory.
It's a simplification.
But even those are just, how do you describe that which is like all over the place?
Right, exactly.
You're just averaging in
So
some way.
what causes radiation? Okay, is it Faraday's law? Full stop. That's it. I'm going to elaborate more. But now, do I understand further beyond Faraday's law? We might have theories. I'll try to explain some later on. So here's the full glory. Probably this is the only equation that I'm going to show here. After a heavy meal like this, who wants to see
I wonder
equations?
we should now we should get bracelets out with
I
this engraved on it.
Exactly, not Maxwell equation.
No.
This one
But although I
here.
like Max.
I know nobody hates Maxwell, but I think
How
that
much for a
it's
tape would
one
you
of
have a
them.
Pi Day in Princeton with bracelets?
That's right.
So simple and elegant, right?
Yes.
But you see, not to
It
distract,
says it all.
not to distract from the subject is that I like to empower the students, especially because the elders are too late to empower. I tell them that it's not that one day there was a divine revelation and he woke up and he said, voila. No, he labored 9 years going to the lab day in, day out, and observing everything around him and recording. You see, this is
That's a good story.
yeah, this is the thing that because people say I'm not as good as he is. He's a giant. No, work hard, observe, and do it diligently. And if you spend 9 years of your life, you change history. Is it worth it? Next, please. So in summary, the physics is that you have a current varying in time creates a magnetic field. A magnetic field varying in time creates a current. As simple as that, to a high school student. And then the problem with our teaching is that, yes, the problem with our teaching approach is that many students or professors minimize the significance of this. So you find literally about maybe 5 pages in a physics book this thick due to this. So the students think that I should grasp it very quickly and jump on to something more. So what do you do in graduate work? Nothing new, nothing exciting in my opinion. Okay, PhD, whatever, but you're not working on laws. You're working on computational techniques. Like in the 80s when
That's because you want to
everybody
graduate.
in the 80s when everybody was doing a method of moments. Who's doing method of moments right now? I mean, people forgot what was the method of moments. It was the mainstay, the whole thing in the graduate. Michigan did a ton of work, right? Volakis. Oh my God. Ohio State, Illinois. But it's not that they were wrong. They did it for the right time, The question is here, is anything physical beyond this? No. Next. Okay, so what about Coulomb's law? We don't want to leave anyone behind. Coulomb's law, 2 charges either push each other or pull each other. Okay, so where in the world did this come from? You see, that's why I say if we leave Coulomb on an island for many, many years, and they're the best, smartest, I don't think they can come up with this. It's impossible.
They'd be lucky to be alive.
With the experiments,
It
if
doesn't
they
have
built
to be
something.
this desolate island in some of the countries that we have today, like in Africa somewhere. When the environment is not
Sure, but my point
conducive.
is that if one is left in isolation, no matter what, that's why I like to separate reasoning versus physics. Reasoning is not physics. We respect people who reason right, but physics is different. Next, please. So, it is somewhat a simplification, I say, in engineering language, this is a model. You see, once these start moving, where's the static field? Right? Gone. Look at this, for instance. Next, please. So here is a lightning strike, it's what? It's the current that is moving, and on the right-hand side we have a simple circuit. When the current moves, then we have radiation. Any more to it? No. When the current moves, there's radiation. Now, I have a theory. I said here electronic current, electrical current, electrons current. It's the same. Current, electrons, charge is moving. And it's really, we don't we don't let the students marvel like this. We just rushing. We are in a society where rush to do what? To recycle the same thing. So if why am I saying this? I'm not exaggerating. If I tell you, for instance, if we look at the breast cancer in microwaves, what have we done? Nothing. Why? How many years have we been working on it? Since the late 80s. Why? We're not thinking in the right direction. You see? So there's a reason why. There is money in it. There's a lot of money. I'll tell you, there's a lot of money. But we're stuck with paradigms. We just don't want to leave them.
But you're right. That gets passed over. My daughter's studying this right now. That gets passed over very fast.
Very fast.
Wait, the electrons are going this way, but the current's going that way.
But also,
but
also you are affecting someone 5,000 miles away by the movement of these charges.
But two thoughts. You have, obviously electrons and holes, but it's a nice shorthand, the area, because you really don't want to have, it's tough to count discrete electrons, but even each one is a little bubble with a field going about its business.
But what is the cause of that field? That's something I cannot answer. I have some theories, I can share some with you. Nobody has talked about.
Yeah, the thing is that when you ask the question in class, the teacher just shouts louder and says the same thing, and so you stop asking.
right.
My son was taking physics, which is this course right now.
Am I
He's
right?
the first year. Of course, the first year of physics. And he studied this, he was happy. He's going to study what his father does. I said, Yusuf, his name, please pause, think. These things changed history. Look, MRI, wireless, transmission lines, you name it, any technology that will differentiate us from 3 centuries ago. What is it? It's just wireless technology, optics, lasers, masers. So I told him, give it some thought. Next, please. So, okay, next, please. This is just to show that we can capture the radio waves. That's how we know the action at a distance. So if you want to look at the magnetic field, what in the world is the magnetic field? It's just a manifestation. Some of the textbooks, by the way, start with Lorentz, the so-called Lorentz force law. And what is the Lorentz force? If you have an electric field, which is E in red, and if you have a magnetic field, which is B, some phenomenon, and you have a moving charge, you get a force. You get a deflection of a charge that is moving. That's how people postulate that missing thing. And they came up with a model. So this Lorentz force law is a model. And I have a serious issue with the word law. I'll explain it in a second. Next, please. So, what about Maxwell equations? I call it a mathematical interpretation of Faraday's and other laws. That's what I call it, a mathematical. So he put all the physics, he's smart guy, he shipped the box, then came out Maxwell's equation. So again, not to be someone who really makes people's life difficult. I asked some of my colleagues. I said, how many equations are Maxwell equations? The quick answer 4. I said, really? They said, yeah, the curl, the divergence. I said, the other 2. Why the other 2 are included in the top? There's no answer. Are they 4? Well, if you go to the commercial codes that are available, they solve 2. What happened to the other 2? So in other words, I can predict the full radiation phenomena using 2. So why do we have 4 Maxwell equations?
Math.
Right.
Isn't that interesting?
My engineering manager told me years ago, as I was doing something on these lines, like, stop that. Ohm's law is fine. Just use
Ohm's
that.
law is fine. Yeah. Produce something.
Yeah, it's good enough.
Yeah. We did not.
We're gonna do whatever. We're gonna get to whatever we calculate and then multiply by 2, and that's it.
We did not have, probably in the back of his mind, we did not hire a philosopher.
No, he's not. No.
You know, but
It was power conversion. It was not this kind of stuff.
I'm going, you know, I like to argue that, you know, once we're an engineer, I think you cannot change your life. You become a problem solver. It changes.
You point out problems to everyone,
Yes.
and they get very frustrated with
Wasn't he
you.
a mathematician?
I'm sorry?
Maxwell, was he a mathematician?
In those days, they did not, you know, Leibniz, Gauss. If you look at Gauss, was he a mathematician? But he did a lot of things we call Gauss' law. So in those days, the divide was not. He was a practitioner. He was a scientist. He did a lot of optics, amazing lenses. You know that he did the so-called grin. It's GRIN, gradient index. He was the first one to come up with it. I mean, the man was prolific. Really, I mean, my hat for him. But I'm not trying to belittle him.
So,
We
but the notation tells you everything. What kind of notation he used?
meaning.
Well, if someone considers themselves to be a mathematician or a physicist,
Well, you know what?
engineer.
It depends if they start counting at 0 or 1.
Yes.
So,
I think that this boxing each other is not the right thing. Can you go next, please? You see, the thing, see, I say all other laws are there.